Hi, my name is Jimena de Leon.
Hi, my name is Laura Ibañez.
Hi, my name is Daisy Luna.
Hi, my name is Lisbeth Salinas, and we'd like to present to you our wind power generation project.
So our purpose was to find ways to replace the non-renewable resources that we are most dependent on, and one way was through wind turbines. So there are two types of wind turbines, horizontal axis and vertical axis wind turbines. Vertical wind turbines are different from horizontal ones in that they implement rotating magnets and coils to capture energy. Our team's goal was to find the most efficient wind turbine design for a vertical one. And we designed and altered different aspects of the Savonius turbine and tested for different models. After 3 consecutive trials, we found the most efficient blade design components by comparing the rotations per minute.
The hypothesis we wanted to test was if the surface area is decreased, then the wind is able to push the blade at a faster rate because there is less of a drag force. For our independent variable, we experimented with blade length, tip length, curvature, material, and surface area. For our dependent variable method of measurement, we used rotations per minute. The vertical axis rotation, coils, the velocity, and distance of wind from the turbine all remain the same. We reference the traditional Savonius turbine design in our prototype models.
On the top right-hand corner, you can see the materials we used for our project, and in the bottom center are our methods. For the initial construction phase, we each used a Savonius turbine as the base for our designs. For our testing phase, we placed the hairdryer 8 inches from the center post and 6 inches from the outermost edge of the wind turbine prototype to maintain a controlled environment. We also set the hairdryer to the highest cool setting, recorded the rotations per minute for 3 30-second trials with the fan on. We repeated these steps for the other 3 prototypes and averaged the results to compare the differences in efficiency across wind turbine designs.
In data for our elliptical prototype, we utilized wooden posts for attic structure and curved elliptical blades, allowing it to reach an RPM of 378.22. For our H-rotor Darius prototype, we used long extended vertical blades, which translated into an RPM of 347.33. For our Darius Savonius prototype, we utilized slightly curved thin vertical blades close to the center, equating into an RPM of 318.67. For our disc prototype, we used 3 curved disc-shaped blades, allowing it to reach an RPM of 311.67. The elliptical prototype obtained the largest RPM. The HR rotor Darius, the Darius Savonius, and the disc prototypes followed. For our results, after testing and observing the following variables, our research showed that the longer blades are more effective. Our turbine kit had auto dowels, which limited the radius we were allowed to work with, meaning it was vital for us to utilize the maximum space for the blades to efficiently spin. In terms of tip length, the ideal tip speed ratio was 3:1, since it decreases aerodynamic stress while increasing torque. For curvature, the slight curvature is optimal as it directs winds towards the center of the blade, unlike flat surfaces that scatter it. For surface area, maintaining minimal surface area improves efficiency. In other words, we included just enough to catch the wind, but not too much as to generate unnecessary drag force. For the number of blades, doubling the number of blades increased efficiency.
Once we tested our prototypes, the hypothesis we developed prior to conducting our experiment proved to be correct. When we decrease the surface area, the wind turbines are more efficient due to minimal drag force. Our contributions to wind turbine research will help scientists obtain more efficient and sustainable ways to capture wind energy through the blades we designed, and it can be utilized to help bring a convenient and clean source of energy to homes and businesses, leading to a decrease in their carbon footprint.
We would like to acknowledge our sponsors, partner associations, and mentors for their continuous support. Thank you so much for watching our video.